hanging in. So, I want to talk a little bit about the exam. That's basically the feedback. Maybe it's going to be useful for your next exam. Question number one, most of the students answered this one. These are the feedbacks from the EAs. So, with the electronic configuration, some students had problems giving the electronic configuration. So you may need to work on it. And again, this is a problem I have been saying for many times. The diagrams are asked. You don't give the diagrams. You are supposed to discuss it based on the diagram. Okay, if you have not given the diagram, then you will lose points. So be careful. Next time for the next exams, whenever a question with the diagram is asked, you must explain it with the help of the diagram. If you do not have that diagram there, your answer is not complete. Okay? So, second, most of you guys answered them satisfactorily. And few brother in law. And one point here is missing explanations of why polycrystals tend not to be anisotropic. Okay, polycrystals are isotropic, right? Yeah. Why? What is the reason? Because you are taking whatever property you monitor. Okay, you are taking the average. Because all in that polycrystals planes are arranged in different directions. So what you are getting is an average. That's the reason why they are isotropic. Okay, polycrystals are isotropic. So there are some students had problems in discussing the interfacial and grain boundary. Okay, and for question number 3, most answers were satisfactory with a few minor mistakes, arithmetic errors. That's the reason why you have enough time. You need to double check your answers, and you are supposed to put all the units there. Okay, you have enough time. So if you are done, just do not leave the whole. Just double check all the answers. And check all of them. That's going to help you. The fourth question, the incorrect were present fuels. Many had a problem with the part B. Several answers used the incorrect formula and omitted the units at the end. The same problem, did not complete the full question. So, question number 5, many students made mistakes with the diffraction angle and determining the interplanar spacing with the equations provided. Again, I mentioned it many times in the class. Whatever you get from the XRD is 2 theta. But in the equation, you are supposed to use theta. Okay? So you need to be careful about those things. So that's the advantage of coming to class. So now about the quiz 2. Again, quiz 2, some of you guys scored full points. And some others, many of you guys got 14, and some of you 13, and it was going like that one. The average score was 68% with a high score of 100%, low of 30%. So for screw dislocation, line and Burgers vector are no. So for the screw dislocation, for the edge dislocation, they are parallel. For the edge dislocation, right? Edge dislocation, you have that moment that is along the same direction. That is parallel. For the edge dislocation, for the screw dislocation, it is perpendicular. Yes.
Will we get the exam papers back to us, or should we double check?
If you need feedback, if you want to see your exam papers, please go to yes. They can show it to you. Okay? I have already announced in the class, I think in the last class I announced it. Okay, if you want to see your answers, please go to GS, they have your answer sheets. And they will tell you what all things you have done there, okay, you can clearly look at it. So now, an ideal catalytic material, you should have the maximum number of defects. Maximum number of defects, that's very important. Why? Because whenever you have defects, that's a incomplete, the energy is higher, so it can absorb more of the material. So that's the catalyst, right? It can take part in that process of that reaction, okay, by absorbing it on the surface and then converting into another thing. So that is the important factor. So in the catalytic converter, your vehicle's catalytic converter, it does the same thing. So in steady state diffusion, the diffusion flux is proportional to
The concentration gradient.
concentration gradient. You know, at least one of you asked me why it is not proportional to diffusion coefficient. Diffusion coefficient is a constant, right? So it is not proportional to diffusion coefficient, it is proportional to concentration gradient. When you write equal to, okay, when you write J is equal to diffusion coefficient into concentration gradient. When you say it's a proportional, it is proportional only to the concentration gradient. For a given material under a non-steady state condition, the rate of diffusion is maximum at which of the following temperature? What is the rate of diffusion? Increases with the increase in temperature. So what the answer you should select is the highest value. Okay? That is the rate of diffusion increases with the increase in temperature. That's the reason why I think 650 was the answer. I think that was the highest temperature. So technique used in the semiconductor industry to get some impurity atoms at 900 to 1000 degrees centigrade in silicon is
Pre-deposition.
pre-deposition. The pre-deposition step. And carbonization of steel to make gears is an example of what type of diffusion? Interstitial diffusion. That is the interstitial diffusion. Okay? So these are some of the feedbacks. You know, others, I think other questions you have scored, most of you guys have scored highly, or 80%, 75 to 80% to 100% answers were correct. Yes.
So for the screw dislocation one, I have written on my notes that screw dislocation is parallel. I remember you told us it was parallel.
No.
It's in the PowerPoint too.
Parallel?
Yeah.
Yeah.
Screw dislocations, the book says, are parallel, and edge dislocations are perpendicular to the dislocation line.
In class I corrected it, right? In class I corrected it. I corrected it in the class. I told very clearly, okay, there was a mistake. I remember now. I told in the class there was a mistake in the textbook. So I asked you to correct that one. I remember that now. Thanks for reminding me. I remember saying that one. Okay. So, you know, I remember I said that that's important too, even for the next chapter, it's important. So, remember, edge dislocation, it is parallel, right? It is parallel edge, you know, you see one incomplete plane, it moves like this one. So, your dislocation line is parallel to that one. Whereas, for the screw dislocation, what is screw dislocation? This is the screw dislocation. That's the reason why it is perpendicular. This class, we are going to learn more about it in the next chapter. So remember that. So, any questions? Now, looking at the next one, the Rockwell hardness. I talked about the hardness measurement. Why hardness? What is hardness?
A measure of the
Resistance
material's
to?
resistance to localized deformation.
Plastic deformation. That's point. You need to remember that point. Plastic deformation. Okay, is the resistance to plastic deformation. That is the hardness. A measure of the resistance to plastic deformation. Here, this is that slide. Resistance to localized plastic deformation. So large hardness means high resistance, and there are two methods. One is quantitative method, and the other one is the qualitative method. So here you can see that you see what you do in this case. An indenter is used, and what is the purpose? You have an indenter, and you apply a force using that indenter onto your surface to be tested, and you measure either the depth of the indent made by the indenter, or another method, if you use a ball or spherical indenter, you apply that force onto that one and then determine the diameter. Okay, or the diameter variation in the diameter of that indent made on the surface. So there are different methods to determine the hardness. One is the Rockwell hardness. So difference in depth penetration resulting from the application of an initial minor load followed by a larger load. Okay, you will see some videos, so you will understand it better. So you have an indenter here. Initially, a minor load is applied, like in the case of this one, for the Rockwell hardness. Okay, remember this. You can learn these things right now. Rockwell hardness, you use an indenter of 10 kilogram. That is the minor load. Okay, we first use a minor load, and an indent is made there, and then you apply a major load, like 60, 100, 150 kilograms. 60, 100, and 150 kilograms. Did you get it? Initially, a small load is applied, which is 10 kilogram. Then a major load is applied, that can vary from 60 to 100 and 150. So now you measure the difference in the height between these two, initial minor load and the second major load. Did you get it? The difference in the depth. Okay, you apply this in the minor load first, then major load, and then you just measure the difference in the height. That's it. Okay, that is the first one. So, in the superficial Rockwell hardness, these are typically used for not that thick material. Not that thick material, not that thick samples. So in this case, what you do is that your minor load is 3 kilogram, right? It is that 3 kilogram, but your major load is 15, 30, and 45 kilograms. Again, it can vary. Okay, it can vary. That is the process. So then what you can see is, for example, for your Rockwell hardness, if there is a value like 80 HRB, what you get is something like 80 HRB, which means that 80 on Rockwell hardness, that is the HR, Rockwell hardness on B scale. 80 on Rockwell hardness of 80 on B scale. Where is that B scale? If you look at this table, you can get that B scale. So whenever that B scale is there, you can see the indenter used is a steel board of 1/16 inches, and that is that indenter used, and your major load is what? It is 100 kilogram. What is your minor load?
10 kilograms.
10 kilogram. Got it? Clear? So that is the meaning. And what about the superficial Rockwell? For example, it is 60 on HR with 30 followed by a letter like T, NTW. Okay, you will see some letters like this one, which means 15, 30, 45, NTW. So we can say that 60 on HR, 30W means 60 on HR, 30W. You see? So this is the, what is the intender? It is 1/8 inch board, and the major load is what? It is 30 kilogram. That's how we can determine it. Yes.
How do you know like what test to use for certain materials?
You can use different methods. Okay, you can use different methods, but converting it is a little bit difficult. Between these two, but of course it is you can use different methods, and what you are doing is determining one difference in the depth, which is it's easier to determine that difference in depth than the depth from the top to that whatever the region. That's the only reason why it is using. But in the other case, it is that the diameter. That's the difference.
Okay.
Okay, so that is the only difference between these two things, and typically that depth, that indent made is very small, so you can still use the sample. Okay, you can still use the sample. So that's the advantage. Yes.
I'm so confused on how exactly the hardest for the material. Does the material have a certain classification, like do we classify it as HRE, or do we test it and then we can
Tested, and you can get those values, but for a given material, for example, a given steel, if you look at your table, you can see this is the hardness. Do you get it? ASTM standard.
But you still need to test it just to verify that it's correct.
Again, that's a very good point. We are going to talk about it later. There can be variation there. And it's, you can test it for particular applications, and still, whenever you make these samples or take these samples for a given application, there can be variation, and even when you handle it, there can be dislocations. So it can vary. That's the reason why we will come to that topic later on. So that is the superficial Rockwell. In the case of Brinell harness, again, a spherical indenter is used, forced into the surface of metal. The diameter is 10 millimeter. What is the difference between these two, Rockwell and Brinell harness? It is, here in this case, the diameter is tested, or difference in the diameter, or the diameter is measured. That is the difference. The standard load is, is 500 to 3000 kilograms in 500 kilograms of increment. Notice that here there is not a minor load. Okay, there is no minor load in this case, but here you have that the diameter of this one is, the indenter is 10 millimeter, whereas the standard load you apply varies from 500 to 3000 kilogram in 500 kilogram increments. I will show you the video, but the other one, then a microscope or digital camera is used to determine that diameter of that indent. Did you get it? You have that spherical board, you make the indent, okay, and what do you measure with respect to that force applied? You measure the diameter. So that is the difference between the Rockwell harness and the Brinell harness. But in the case of loop and Vickers microindentation, it is a microindentation. Okay, remember this is a microindentation. You can see why it is applied load range between 1 gram and 1000 gram. You see, that is the difference. It is 1 gram, the applied load range applied load ranges from 1 gram to 1000 gram. And where is more diamond indenter having pyramidal geometry is used. Okay, that here in this case, diamond indenter is used. So that is the new and biggest micro indentation. Diamond indenter is used, and the load ranges between 1 gram and 100 gram. And here in this case, you have the careful sample preparation is necessary. I will show you the video after this one. So hardness number for the Rockwell hardness, that is the difference in the depth of penetration. I have already talked about this one. Initial and minor load followed by major load. And the Brinell hardness number HB is a function of magnitude of the load and the diameter of the resulting indentation. Okay, and the relationship between tensile strength and hardness. You see, tensile strength, they are more or less similar. Do you agree? What is the tensile strength? You apply a force, applied force versus
the strain, the change in force.
Stress into stress versus strain. And you have that curve. At some point, plastic deformation starts. And if you still apply, what happens? It reaches a maximum point, and that maximum on that stress strain curve is
the tensile strength.
Okay, tensile strength. There also you are applying that load, right? Stress means load. Agree? Yeah. Stress is the load. So you can see that is the maximum. So they are related. So what is your hardness? Hardness is also the resistance to plastic deformation. Do you agree? That is the resistance to plastic deformation. Therefore, we can say that they are related. Okay? They are related, and the relationship is the tensile strength in megapascal is equal to 3.45 into Brinell hardness. Okay, this is a relationship between this tensile strength and Brinell hardness. Okay, 3.45 in HB.
The Rockwell hardness test, scale C. In this video, we will show how the Rockwell hardness test works using the gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant scale C, a rounded cone made of diamond is used as an indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point. In step 2, the test force is increased by 140 kilopons, which is acting as the major force. This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters times 500. Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it. The Rockwell hardness of our gear wheel is 55 HRC. This result is displayed on the screen.
Okay. So the other one you can watch it at home. The other two is already given in the slide, so please watch it at home. The other two. The Brenner harness and the Vickers harness test, the videos are given there, so you can watch them at home. So, design safety factors. Okay, this is also very important that design safety factors. Basically, he asked that question initially. You have a sample, and the sample can have defects, right? It is very hard to control the number of defects in the sample. Agree? So whenever, as I said, whenever you handle it, there can be defect on the structures, there can be scratches on the surface. Okay, you will see in the next chapter, all the scratches and even the minor defects in your sample can be catastrophic. So that's the reason why you need to be very careful when you design something. As engineers, you should be really aware of these type of things. What happens when you design a structure with the materials, there can be always defects in the system. And the 20th century approach was, to use a sample, okay, with a strength much higher than that required. Okay, higher than that required. That was the strategy. Did you get it? If the tensile strength or the yield strength is given, for example, 100 megapascal. Okay, and for a given application, use something with 150 megapascal. Okay, yield strength. So you are sure that it is strong enough to sustain that load or whatever application required. You got it? That was the 20th century approach. So in that case, you can see that there is a design factor, okay, safety factor. Okay, this is that safety factor or design factor N. Often the value of N is between 1.2 and 4. So this is the working stress and this is the yield strength. And the value is between 1.2 and 4. And from this equation you can see that the working stress is always less than yield strength. Okay? Since it is between 1.2 and 4. So that was the approach. But the 21st century approach is different. So a redundant structure is used, especially for space applications and all. But we cannot afford any failure, right? For a space application, this is going to be very expensive, catastrophic, and all those things. All those factors you need to consider as aerospace engineers, you need to consider all these factors. So that's the reason why the use in 21st century approach is, even if you need to still use that material with high yield strength or tensile strength and all. On top of it, you need to have a redundant structure, which means even if one structure fails, critical components, okay, critical components. So the other one, the second one should withstand whatever that load is. Okay, that's the approach. So from this one, you can see that from the stress, the general equation is this one. The working stress is sigma y over n. We still use it. Okay, that 20th century approach, we still use it. And in this case, you see less critical static situations. Design stress sigma d is equal to n prime into sigma c, where sigma c is calculated stress and calculated stress. So n prime is the design factor, so which is greater than unity. So your design stress is equal to n prime into sigma c, calculated stress into a design factor for less critical applications. So now for most of the applications you use this equation. For example, if you have a road, a structure, a road like this one, this is the example. Calculate the diameter d to ensure that the yield does not occur in 1045 carbon steel road below. Use a factor of safety 5. The question is calculate the diameter d. And here is your road, okay, 1045 steel road. You are asked to determine this diameter. It is given like sigma y, yield strength is 310 megapascal, tensile strength is 565 megapascal, and the force applied is 220,000 Newton. So how can you determine that one? Your safety factor is given as 5. The equation is sigma working is equal to yield. This is the equation. Yield strength over n. It is asked to take the safety factor. The question asks to take the safety factor as 5. So how can you determine the diameter? We know that sigma is force applied per unit area. So force applied per area. So we can say that this is force is given as 220,000 Newton. So 220,000 Newton into pi d squared over 4. That is the area. So from this one, we can calculate. Calculate the sigma y is already given there. Yield strength is given as 310 megapascal. You need to convert it, okay? To Pascal. So then N is given as 5. So you just need to substitute it, and you can get a value of D is equal to 0.067 meters or 6.7 centimeter. So in this chapter we have talked about the stress and strain. Stress is the force applied per unit area, and strain is the elongation, that is change in length over original length. What is elastic behavior? Elasticity, it goes back to the original one. So that elastic behavior, whenever you apply a force, when you release that force, it goes back to the original one. What is plastic behavior? Permanent. Plastic behavior is permanent. So toughness, how we can say somebody is tough?
It's resistance to it's resistance to plastic deformation. What hardness is.
tough person. I talked about that tough person at that time.
It can undergo a certain stress and strain, but then it can come right back. The material's ability to come back. Wait, resistance to fracture. Resistance to fracture.
So what is it? Even if there is a fracture, even if there is a defect in your system, okay? Even if there is a defect in your system, it is still tough. That's the meaning. It can still sustain that load. So that is the meaning. So you need to remember that one. That is a tough person. Even if something happens to a person, it can still sustain that load. That is the whole meaning of the toughness. Okay? Agree? So you are going to talk about that crack, crack and how resistant it is. Whenever resistance of that material, that is that meaning. The whole meaning of a toughness is whenever a crack is present. That is the point. Whenever there is a crack is present, still it can hold on. That is the meaning. That is the whole meaning of the toughness. So the ductility. The toughness and ductility are related. Agree? What is ductility? Plastic strain at the failure. That is the ductility, that is the area, very good. That is area within the curve. Right? So your stress strain, very good. Very good. That is that area. Do you get it? Are you imagining that one? We have the stress strain curve, and what she says is that stress strain curve is like this one, and finally it breaks. So it can withstand it until then. But whereas a brittle material, now what you need to remember these steps. Brittle material, what is the brittle material? It may be, it can withhold maybe a lot of stress, right? But it breaks right away. Whereas in this case, it holds it all the way to that fracture. Okay, that is the difference. Is it clear? Any question? If you have any question, please ask me right now. Yes. Ductility. So that is the measure of the plastic deformation. Ductility is a measure of the plastic deformation. That's that area within that range. So, for example, consider your ceramic. Very good question. We can go from the next chapters. We are going to talk more about these things. So, ductility is the plastic deformation. Example, consider ceramics and plastic. If you try to bend it or bend it like this one, what happens to a ceramic? Think about a very, very thin ceramic plate. It breaks right away. Right? So there is very little plastic deformation in that case. Whereas you have polymer, for example, this one. If you try to bend it, what happens? It is still bent, right? That is the plastic deformation. So why? There is another word I said along with the ductility. What is that word? It is forgiving. Forgiving samples. Why? Because even if you bend it, it forgives that applied stress. So it's a forgiving sample. Yeah, that's the reason why it is plastic. It doesn't go back. Elastic means it goes back to the original one. Whereas the plastic, but still it keeps that one. So what is the reason why ductility is important? What ductility is important? Basically, you get a warning. Okay, if it breaks right away, think about a bridge. Think about a bridge. If it breaks right away, what happens is very catastrophic, right? Whereas, if you have a warning, if you look at the servicing, that's the reason why service is so important. Periodic service is so important. basically, if there is a bend there, you can see that, okay, there can be a failure soon. So your approach should be, you need to replace that structure. That is the importance of service. Okay? So periodic service, that's the importance. So now, let's go to the next chapter. So this looking at deformation, strengthening and strengthening mechanism. So that's what we are going to talk about in this chapter. Why are dislocations present? How are strength and dislocation motion related? Why does heating alter strength and other properties? This is what we are going to see in this chapter. Deformation and the strengthening mechanism. So dislocations in materials. You have metals, okay, where you have so metals. Here you can see copper, aluminum, silver, all these type of materials. They are all metal. In the second chapter, we talked about the metallic bond. What is a metallic bond? Metallic bond is ions in a sea of electrons. In a sea of electrons. You need to remember that. That is a metallic bond. And what is the characteristic of metallic bond? Is it directional or non-directional? Non-directional. So now look at this one. Since the atoms are in a sea of electrons and the metallic bond is non-directional, okay, is it easy to undergo slip? We are going to talk about that slip later on. But again, I am just saying a slip in general, okay? In general meaning. Is it easy for that atoms to slip in the case of a metallic bond or an ionic bond? What is ionic bond? Ionic bond in all the ceramics. Like sodium chloride is an example of a ceramic material. Okay, aluminum oxide or those type of materials. Mostly it is the ionic bond which is easier for the plane of atoms to slip. Is it metallic bond or ionic bond? Slip the atoms. Metallic. Why metallic and non-ionic?
Because of the positive ion cores.
That is basically because remember the sea of electrons. You have that metallic core in an example. This is a plane of atoms. Assume that this is a plane of atoms. This is another plane of atoms. And what is in between? Sea of electrons. So it is easy for this plane of atoms to slip, right? Move from one point to another point. Do you agree? Do you agree?
Yes.
It's like a lubricant. It's like a lubricant. You can move this one. So once you have this plane of atoms move from one on top of the other, what is that process called? That is the dislocation. You can consider it as a dislocation as well as it is the movement of the planes. So the dislocations can move from one point to another point like this one, and that is a plastic deformation. Agree?
Yes.
That is a plastic deformation. Okay? So this is the process by which the atoms move in a metallic material. So metallic material, they are strong. We know that metallic materials are strong, and at the same time, metallic materials can be ductile. Agree? Because of this movement of the plane of atoms, it can be ductile. So that's the reason. It's a very important property which we all need, right? In many of our structures, this property is very important because you need to have strength. Because to get strength, you can have other ceramic. You know that ceramic materials are very strong. But the property that lacks there is what? The fluidity, plasticity. Okay, plasticity. That's the reason why most of your materials, even if the strength is not as much as that of the ceramic material, we use metals and alloys for making most of our structures. That is the reason. So that is the covalent bonds and ceramics. Ceramic material can also have the this one. And here in the case, what is the characteristic of covalent bond? It is a directional bond, right? This is non-directional, and ionic ceramics, it is non-directional. Because why? Because you can see that all of them are connected like this here. Between them, positively charged and negatively charged, they are all connected to each other. It is non-directional, and but the problem is, it is extremely hard for these atoms to move in ionic bonds. That is the difference between this one and this one. Metallic bond and ionic bond. Yes?
It's easier for non-directionals to slip because they can move either direction.
Yeah.
And then as far as between ionic ceramics and metallic bonds, it's easier for metallics.
It is easier for metallic to move, but for the ionic and covalent, okay, covalent is directional and the ionic is non-directional. But even though the ionic is non-directional, but the problem, we know that ionic bonds are very strong bonds. Positive cation and the anions are attracted to each other, and they are strongly bonded. It is extremely hard for you to separate it. But whereas in the case of atomic bond, it is ionic core in a sea of atoms. Yes.
So the stronger bonds are
Yeah. Yeah, because in the case of ionic bond, that is exactly what is the attraction between the positive and negative one. Okay, so now dislocation motion. We know that what is a edge dislocation? Edge dislocation, remember, a half plane is present or an incomplete plane is present in your material. Think about your metallic material. You have these metallic bonds, that is considered as a plane of atoms or an arrangement of atoms like this one. And in between you see this, this is a half plane or an incomplete plane. And what happens? This incomplete plane, at some point, these atoms can move to here, and these atoms can move to here. And what happens in this case? This becomes half plane. The B plane becomes a half plane. Did you get it? How we can get it is that from here, this atom can bond here or bond with this one, and that incomplete plane moves from this point to this point. Look at this one here, it is moved from this point very easily. Now, this can continue until it reaches one of the ends. Okay? Okay? That is the reason why this is the edge, this is moving all the way, and finally it reaches an edge where you see this is the one step of a slip. Got it? Clear? So this is how edge dislocation moves. Half plane moves to the next one, to the next one, to the next one, and finally it reaches one of the ends of that circle. Do you have a question?
I was gonna ask, like, how often does this, like, happen?
Very good question. It can happen, and what is the requirement here? Your activation energy, right? If the activation, always remember, if you want to go from this point to another vacancy there, then it should be, you have that energy to move to that point. Then only it can happen, but it can happen. Basically, the energy is even from the room temperature, that thermal energy is there, right? Because of the temperature, the thermal energy is there. So this can happen very easily.
Now, does it happen like a lot on a smaller scale, or like when it happens?
It happens a lot at the microscopic level. Okay, in some cases, when you hold some samples, for example, silicon industry, for the semiconductor industry, where, this shear stress can be, whenever you hold it with a tweezer, it can exert that force, that shear stress onto this one, and it can move those plates. That's the reason I said previously that it is very easy for these dislocations to take place, and it can move from one point to another point. So that's the motion of the dislocation, and if this is prevented, okay, so whenever you have a plastic deformation, your strength is getting reduced. Do you agree?
Yes.
The strength is reduced whenever you have that plastic deformation. So how to strengthen the material? We will talk about it later. How to strengthen a material? By preventing the dislocation to move from one point to another point. Agree? Are you with me?
Yeah.
So that is the strengthening mechanism. If you want to strengthen a material, what you need to do is, you can prevent that motion, dislocation to move from one point to another point. That is a strengthening mechanism. That is, if dislocation cannot move, plastic deformation does not occur in the sample. So the process by which these dislocations move, that is called the slip. For dislocation to occur, that is the slip. So, we just talk about that the slip, the process by which plastic deformation occurs by dislocation motion, that is a slip. And what is the slip plane? Crystallographic. So crystallographic plane along which dislocation line traverses, that is called a slip plane. So a dislocation moves along a slip plane in a slip direction. Okay, so you know that for the edge dislocation, for an edge dislocation, what is the movement of this one? This is along this direction, right? So that is the crystallographic plane, movement of that plane. What about the screw dislocation? This is the direction of motion. So you have that plane, and that's how that dislocation moves along that direction. Okay. Got it? Here, this is the direction, and we can say that if this is the direction, this is the direction along which, this is the direction along which that dislocation plane moves. And what about the other one, screw? This is the direction that is perpendicular, right? It is perpendicular. This is the direction along which that dislocation moves. Okay? There is a dislocation line and a plane. Yes?
Is slip related to shear?
Slip related to shear?
Yeah, because it seems
Yes,
to have.
that is a shear force.
Okay.
You know, remember that's the reason I talked about that semiconductor industry. Even when they use a tweezer, you know that slip can occur, and that's the reason why in semiconductor industry you just use a vacuum mother. You just use a vacuum hand, you know, of the robot to move that silicon wafer from one point to another point, like this one. Move it like that. Yes.
What does it say after dislocation?
Line traverses. You know, that is the dislocation line, right? Everyone. You see, that is, what is the edge dislocation? What is, if this is the edge dislocation, what is the line of dislocation line? This is the one, right? So remember, this is the half plane moves in this direction, and that is the direction of dislocation direction. And that is the plane along which that moves, and that is called the dislocation plane. So dislocation density. So dislocation density is total dislocation length per unit volume. That is called dislocation density. In a given sample, the total dislocation length per unit volume. So, for example, it is a unit of millimeter of dislocations per millimeter cube. So this is the dislocation length in millimeter, and a volume is millimeter cube. Or it is the number of dislocations intersect a unit area of random section. For example, if you have a unit area like this one, and it is the number of dislocations hitting this cross-sectional area. Okay, so it is the number of dislocations per unit area. So random section or random area of that 1 millimeter square. And the heat treatment can reduce the density, dislocation density. Okay, remember that heat treatment can reduce the dislocation density. How? You will see it later. You know, if there are two dislocations, okay, under normal conditions, room temperature, in order for a dislocation or a slip to happen, the dislocations should move. So if there is one dislocation at this point and another dislocation at this point, assume that under normal conditions, normal temperature, this cannot move. But as the temperature increases, as the temperature increases, what happens? Energy is higher. Remember that similar to that activation energy. The activation energy increases, similar to that one, okay? What happens? You enable that dislocation to move so that it can recombine. Okay, don't worry about that recombine. I will show you how the dislocations recombine. Think about it. This is a half plane here, somewhere here on top, and this is a half plane somewhere at the bottom. If they move like this, what happens? Annihilation happens. Agreed? Now it's a single complete plane. That's how the annihilation happens. And that's the reason why, as the temperature increases, the number of dislocations decreases. Because of the easy movement of dislocation. For ceramics, it's about, again, 10 to the power 2 to 10 to the power 4 per millimeter. And for single crystal silicon, the value is about 0.1 and 1 per millimeter square. So 0.1 to 1 per millimeter square. That is the dislocations and density. Now you have the consider this one. You have a, what is this one? Edge dislocation. This is an edge dislocation, which means that there is an additional half plane or an incomplete plane present in your sample. And you can see that at this here, the atoms are squeezed together because of the presence of that half plane. Okay? All the atoms are squeezed together. And what type of force is there when the atoms are compressed? There is a compressive strain on the sample. There is a compressive force or compressive strain or compressive stress on the sample, and there is strain too. So here, what about here? The atoms are pulled apart. Okay, atoms are pulled apart at the bottom, and then tensile strain. Here you have tensile strain. Since atoms are pulled apart. Whereas here, atoms are squeezed together. And there is a compressive strain here. Got it? Clear? So you have this compressive strain here, and there is a tensile strain at the bottom. And you know, whenever you have a compressive strain and another compressive strain here, you look at this one. One, you know, where you have a plane of atoms. Here you have a compressive strain, and here also there is a compressive strain. And there is another one at the bottom, another one at the bottom. So what happens in this case? Just imagine like a positive, and a negative. Just assume it like that. It's like a positive, and negative. What happens when you try to move them closer and closer? There is repulsion, right? And what happens when you have a positive here and a negative here and a negative here and a positive here? Attraction. So this is what I talked about before. Dislocation, annihilation. So that dislocation is gone. It is annihilated. They combine together. These two combine together, and it leads to a perfect crystallographic arrangement. It's exactly like what I said before. There is a half plane at the top, and there is another half plane at the top. At the bottom, then you have here in this case there is compression on top and
Repulsion.
what is here? Tension. Compressive strain and tensional restraint at the bottom. Whereas in the other case, it is tension at the top and compression at the bottom. When they come closer, they can combine, and that is related. So for screw dislocation, lattice strains are pure shear only. We learned about it. It is the shear force, right? For that screw dislocation, it is the shear force. Now, a slip system. So, a slip system, what is a slip system?
Combination of the slip plane and slip direction.
So, that is very good. It is a combination of slip plane and slip direction. That is a slip system. So, slip plane is the preferred plane along which dislocation motion. This is the preferred dislocation plane. And what is slip direction? Preferred dislocation direction. Preferred dislocation direction. Now look at this one. Here you have a face-centered cubic structure, FCC structure. And for our FCC structure, what is this one? The plane that goes from here, from this atom on here, and along this direction to this atom on this side, and it goes along this one to the other side, this F. And what is this plane?
111.
111. This is a 111 plane. We use x-axis 1, y-axis 1, and z-axis 1. So, in this case, in this plane, this 111 plane, the direction, this is a plane, 111 plane, and the direction, there can be 3 directions in which this slip can occur. Okay, this direction, or this direction. Again, if it is in the other direction, it's the same. That's the reason why we consider it as 3 directions in which the dislocation can happen. Okay, so what does that mean? A slip plane and all the slip directions that constitute, this is a slip plane, and there can be for each slip plane there can be 1 direction, 3 directions. Okay, one plane there can be 3 directions. So how many one planes can be there for this unit cell? There can be 1 in this direction, there can be 1 which starts from here, another one from here, and another one from here. Agreed?
Okay.
4 slip planes, one planes. Yeah. So each one has 3 directions, and there can be a total of 12 slip systems. Total of 12 slip systems in a face-centered structure. Why we consider the 111 plane here? Because that is the plane with the highest number of atomic density. Okay, that is the reason why 111 plane is chosen here. You see, there is 1 atom here, then it passes through the center atom here, another plane, this it passes to another atom here, another atom here. So that is the slip. The slip plane is the plane along which there is maximum density of atoms. planar density. Okay, got it? That's the reason why 111 plane is the preferred plane, and for there can be in FCC system there can be a total of 4 111 planes, and for each 111 plane there can be how many directions? What is this direction? Any direction here. This is 110, right? This direction is, the x-axis is 1, y-axis is 1, and the z-axis is 1, and y-axis is 0. So that is 110. That's the reason why it is given as family of planes. You see, this is family of 111. 1 is the family of planes, and what is this one? This is the family of directions. 110 family of directions. Okay, so in an FCC system there can be total 12 slit systems. Any questions from here? Yes. Direction? Yeah. Look at this one. This direction. Oh, we are considering the family. And another one, this one. Again, there is no C component, 0. But they are all same family, right?
So, split systems only occur for FCC, they don't occur for GCC.
We're coming to that. It occurs for all those things, all the crystal structures, but it differs. So, if you look at that slit systems, that's exactly the question he asked. So, how many number of slit systems for face-centered cubic? It is that 12 slit systems. Whereas in the case of body-centered, there can be 12, 24, 12, 24. And depending on what type of material you have, it can vary. And for HCP structure, you look at this one, 3, 3, 6. So now, listen here. Can you predict? My question is consider HCP, crystal structure. HCP and HCC. We already learned about FCC. And those are BCC also. You can see it is 12, 12, 24, that type of slit system. My question is, in general, okay, in general, which one is more ductile? FCC crystal structure or HCP crystal structure?
FCC is more ductile than HCP because it has that.
Yeah, you can tell the answer later on. Any other answer? It's basically because I want others to think. Okay. What do you say? Somebody to just say something. There's no problem. I just want you to make you guys answer. That's the only reason. Okay, I am not picking anyone or anything. So just want to get that response. That's the only thing I am asking. Yes.
BCC because there's more slip systems.
And I'm not considering BCC right now. My question is HCP and FCC.
Then it would be they're the same number, so you can say like
Ductility for both FCC and HCP are the same.
yeah.
Why?
Because they have the same number of slip systems.
No, this is the HCP is this one.
Yeah.
And you see FCC is this one. Here you see, do not take the total.
Oh, okay.
Do not take the total. It's a given system. So it can have what's the 0, 0, 0, 1. For this system it is 3. For another system it is family of plates. Okay, another system it is 3, another 4, 6. So just consider either 3, 3 or 6. So which one has FCC? You are all on the same page, right? Why? As the number of slit systems, very good. As the number of slit systems increases, ductility increases. The ductility increases. Why? The reason, because ductility is the movement of the planes. So as the number of slip planes increases, the chances of moving those planes also increases. And that's the reason why ductility increases as the number of slip systems increases. Yes.
So that means that the only way that a BCC is greater than an FCC if it's in a 3-2 ball.
Yeah.
And
For a given material. For that given material.
Anything else would be the equivalent. Because they'd be exactly the same because of what's right.
It's book 12, you know. Again, there are other factors too. It is not completely this one. There are other factors depending on the strength of the bones and all those other factors. But considering everything else the same, that's what I'm asking. Everything else the same if you compare these things. So the FCC is more ductile than HCP structure. So I think, I will stop with this slide. So for slip Burgers vector and direction corresponds to the dislocation slip direction. So magnitude is equal to the unit slip distance